Okay, we're going to come back to a little slideshow. Stuff happens, and sometimes it's that your phone goes to sleep or your phone gets interrupted by a call, and sometimes you just knock it off. So if the most difficult thing in life were just that we didn't have a camera person, I guess that'd be pretty good. We're talking about mapping Earth. We've pretty much done it. I want to show you something really cool, but before I do that, let's review. And so I didn't get to this point. Remember that line? Get that reflection out of there. Oh, okay. The line that we use for longitude goes through London, Greenwich, and that line. Notice that line divides Earth. Notice the equator divides Earth into a north and south half, but the line going through Greenwich, where we call longitude equal to 0, divides Earth into a east and west half, doesn't it? And so we call that the prime meridian. The prime meridian. And so it's just getting to know map it. Remember this? Remember, that's the prime meridian on Earth. This was the meridian in our sky. Remember, this is us standing. So when I talk about your sky, the meridian goes like this. Remember, it goes up and around. I'll show that to you. That's the meridian. It goes, divides it into east and west, our sky. This divides Earth into east and west. If, of course, I do this, and now that's north, then it flips, wind. Still, the meridian goes up and over and connects north and so to south, dividing our sky into east and west halves, the meridian, the prime meridian, dividing Earth into east and west halves. And we're going to see something that changed the world, but I think we will take a little quick, super quick, little slideshow here with sound effects. And go in. And yeah, I know my drawing wasn't as good as this, but I did it by hand. So there we go. Good enough. All right. So you can find stuff like this on the internet. And I'm going to show you something else you can find. What are those called? Cardinal points. What's eye level? Horizon. Some people call it here, but it really works better to be eye level. Where's the azimuth? Going 0, more and more, 10 degrees, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 180, 190, 200, 210, 270, 280, 290, 300, 360 is back. So that's the azimuth. So that's around. And then up. Well, up we talked about zenith, straight up. And then we talked about the meridian going north to south, south to north, dividing it into east and west halves. And then we talked about a particular angle up as the altitude. We're going to use this. We're going to use this to navigate the seas, but it'd be nice if we... Notice that we can divide up. There's a map. These are lines of what? The same, all these places have the same what? The same, they're the same amount north or south of, there's the equator. Right there. North of the equator, south. These lines are all the same amount north. Tropic of Cancer, Arctic Circle, Antarctic. Anyway, and then these lines are the same amount east or west of where? It's weird. They didn't even go through Greenwich, London. It should be there. I guess they have it 0 here, so it's marked 0. And then how much east you go from that line or west. And so, you see it. Earth is mapped out like that. Cool. So Latitude. Oh, I visited there. That was last year when my hair wasn't blonde. Yeah. So we're going to talk about Polaris and how important Polaris was for the course of human history, and for better and for worse. So let's talk about Polaris. And when we're thinking about Polaris, you might ask yourself, well, hey, how far away is Polaris? And I just want to point out, now this is another class, I just want to point out too, that Aristarchus, look him up. We're talking a couple thousand years ago, people were doing some pretty crazy things. They were taking measurements. They couldn't see this. This is seen from space. So when you draw this, you're imagining the way it would be when you draw your pictures. Of course, everything we see is from Earth. But you can play with this, make measurements, do some geometry, and yeah, you're probably glad that I'm not having you run through all this mathematics, right? But it can be done. And it, you just got to put in a little more time and be ready for that. What I want to do is do this. Polaris distance from Earth. It's the same distance from Earth as it is from Sun, because Earth and Sun are really close compared to the distance to stars. Really close. Okay, we'll take that. Now, distance is tricky, so you might see different numbers, but 434 light years away. How did Polaris change our world? Changed it because finding the latitude in the northern hemisphere can easily, relatively easily be done. So go over here to get rid of that glare. And you got to remember two things, and that's why we reviewed that. Two things: latitude and altitude. Latitude's about how far north to south of the equator. Altitude is about the angle up from your horizon. Let's take a look. So, I'm going to make a list here, and you'll find it in your book. Chop off down here, because we've got to be in the northern hemisphere anyway, so if you don't mind. And I'm going to say what your latitude and then I want to look at the altitude that you see Polaris. That is, what's the angle up from your eye level that you see Polaris? And that's why it's important to do eye level, not ground. It really is. So let's do that in my kingdom for my hands in red. Altitude you see Polaris. Alt, you see Polaris, the North Star. What's the apparent magnitude of Polaris? Review that stuff, right? So I'm not going to even tell you. You go back and review that stuff, and you should know that. It's not super bright, but it's brighter than things in this neighborhood. So, and where is it? Well, it's like ridiculously far away, okay? So it's way, way out there. 434 light years. 1 light year is like 1,500 times farther than Pluto, super roughly. 63,000 AU, you know this. So it's way out there. I'm just going to draw it up here if you don't mind. Whatever. Polaris. So really, you'd shrink it to a dot and you'd say up. So if I want to look at Polaris here, it's up. Not there. I don't point there. It's up. And that's an important thing for chapter 4. When things are really far away in my drawing, I can't draw them. If it's up, then I look up because I'm on a tiny thing. Up. And I still look up. That's how I see Polaris no matter where I am. That's important, okay, as we go on, because it's so ridiculously far away. 400 and, let's write that. It's fun number, 434 light years away. You can tell your friend. That means the light you're seeing has been traveling for 400. Where does that put us in history? What was going on in the U.S.? Interesting times, right? Interesting times with slavery. And then as you proceed, and it wasn't as long ago as one might think, when we had the Civil War, when people were heading north, how did they know where to go north? Right? So we're talking about mid to late 1800s, Civil War, And then Jim Crow laws for about 100 years, 1968, right? It's just not that long ago. And for some reason we have trouble seeing ourselves as cousins and taking people for who they are. Anyway, I digress a little bit, but following, if you're gonna navigate the seas, you better watch Polaris. If you're gonna try to head north for emancipation, then you better follow Polaris. A lot of reasons to follow Polaris. How does that work? It works like this. Check it out. It's really not that bad. Let's say I'm up here. Where do I look? What altitude is Polaris? Remember, altitude is the angle up from your horizon. So this is a nice review. Let's draw. Okay, she's at North Pole, and I used red, so I'm going to draw her red. Super tall. She thinks it's a flat Earth because whatever. All right. Let me make Polaris. I can't make Polaris green because there are no green stars. Well, they don't look green, at least. Don't do that. Polaris. Notice for you, this is your horizon, right? So what is the altitude of Polaris? When you're at the North Pole, at North Pole, might as well write it, is 90 degrees, right? Oh, wait a minute. Let me write that again. Wait, let me do it down here. The altitude you see Polaris is 90 degrees. Oh, what's the word when something, what's the altitude, what's that direction when the altitude is 90 degrees? What do we call that straight up? Zenith. But it isn't always there, right? It's only there when you're at the North Pole. What's your latitude at the North Pole? What's the latitude of the equator? How much north or south of the equator is the equator? It's not. Little review, right? Review. And using this is how you remember it, not by staring at it. 90 degrees, or plus 90 degrees if you want, or 90 degrees north, whatever you want. That's a little redundant, but okay. So that means that your latitude is at the North Pole is 90 degrees, or plus 90 degrees, or 90 degrees north, whichever way. Huh, wait. So where you are on Earth, 90 is 90 degree latitude, and the altitude you see Polaris is 90 degree altitude above my horizon, my zenith. Well, I wonder if that works at the equator. So let's travel. Now, I know where my latitude is, so let's just throw that in. Latitude, equator, 0. I wonder what the altitude is that I would see Polaris. Trust. Yes, we're working still. Polaris is way out there, 434 light years away. Crazy. And is that a far star? No, not really. That's really close in our galaxy. We're how far out? Let's review. Always review. It's a barred spiral, so this model's wrong. We're about halfway out. And 434, that's that little neighborhood right there. It's really crazy. Okay. Where is Polaris? I'm going to show you the wrong answer. Remember what you're looking for. Well, let's do this. Here's your ground. Here's your horizon, right? Eye level. It's a good definition. So where's Polaris? So you might go, well, Polaris is here. That's wrong. Wrong, wrong, wrong. Why is that wrong? It's wrong, 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 wrong. Wrong, wrong, wrong. Imagine, remember what we did with the angles. This is a big thing to understand. It's not, you got to work at it, but it's cool, right? Because if Polaris were, say, here, and then as it gets farther and farther away, notice that that angle reduces. It's going to be so far away, where is Polaris going to be? That's a very important idea, right? In my drawing, I had to draw it there. I couldn't draw it 434 light years away. In which case, I would see, bam, Polaris on the horizon with an altitude of what? Well, how much above the horizon is the horizon? There's an angle. There's 90, less, 0. And so the answer is 0 degrees on horizon. What if we're in San Francisco or anywhere else? 38 degrees. We stand that way because down is this way. There we are. Gotta draw it. Gotta draw it. You got this? It's the last bit. Once I figure out, oh, there it is. This is my ground, right? This is my horizon right here. Eye level, parallel to the ground, horizontal. Well, what angle, where do I see Polaris? So I'm gonna put that over here. Let's do latitude, and it works for latitude SF, and it's gonna be the latitude of DC, and that's gonna be 38 degrees north, or positive 38 degrees, whichever way you want to do it, right? So that means if you go to DC, you can have the same latitude. Not only will you see the way that you can check that at night if you've got a clear sky, is measure the altitude of Polaris. Let's go backwards. Let's work backwards. What would we guess the altitude of Polaris is? Well, if our latitude is 90, the altitude is 90. If our latitude is 0, the altitude is 0. You got to study this picture. If our latitude is 38, the altitude of Polaris is 38 degrees above our horizon, right? But that's what altitude means, is angle above the horizon. So that means that if this is true, we have to check it, but if this is true, then you can always know your latitude by measuring the altitude of Polaris. Let's check. Where is Polaris? Is this right? Or is it right there? Just a little light? No, right? Remember this. Polaris is that way. This is such an important idea going forward, okay? We're going to use this. You got to get this. Polaris is way out there. So this is where you see Polaris. What angle above your horizon? You bet you. An altitude of 38 degrees. We're reviewing. We got some more to review. A couple more things. What's the other one I was going to do? 2. Okay. 38 degrees, that's approximately 48 degrees. How can I know that? Well, you can put one of those on your belt and look really cool, or you can do this. You don't even need this stuff, right? Here's my horizon, eye level, make that level, put a little level, a bubble level, that'd be kind of way too cool. And then you go, there's Polaris. There's Polaris. If Polaris is there, I'm on the North Pole, I better get a jacket. I'm on the equator. I'm in San Francisco. Wait, 38, let's call it 40. Eye level. What's the angle from here to the other side of my fist at arm's length. 10 degrees, 20, 30, wait, okay, 40. And I happen to know in this room it's over there. Day and night, that's where it is. I just go like that, eye level. Try not to do, it's kind of tricky, you gotta get used to that. That's 1, 2, 3, 4, there's Polaris. Why? Because my latitude's 38. And it's gonna be 38 above my horizon. My latitude is 38. So the altitude of Polaris is 38. I know, it's tricky, right? But imagine this. Finally, the last point, I promise I'll stop. There's Polaris, right? If you're traveling north, you're gonna see the altitude of Polaris increase. So you know you're going north. That's how you know you're going north. Well, Polaris is going up, I'm going north. What if you go south? Polaris, remember Polaris is straight up, so I gotta do that. The altitude is going, now if you're traveling south, the altitude of Polaris, how high above the horizon, gets lower. And then I know if I'm heading, am I heading the right direction? I want to go south. Oh, okay, well, make sure that the altitude of Polaris decreases. What if we want to go just east and west? Well, then the altitude should not change, right? And you can be picky, like we showed even thousands of years ago. Some folks were quite picky. Oh, you hate me, don't you? Because I didn't do that. All right. Sorry. And there we go. That's the punchline. You have it in the book, so hopefully you have the book open while you watch this. And that pulls together so much, right? Where you are on Earth affects what you see. She can't see anything down here, right? Ever, because she's rotating here. Here you spin around, and so you've got this cone. You've got all this stuff, this cone, this wedge, if you will, that you cannot see from San Francisco or DC or anywhere at 38 degrees latitude. There's all this stuff down here you don't see from that latitude. This one's kind of cool, right? On the equator, you get to see all that, but you come around and now you get to see all that. So as you go around the equator, you get to see it all. But you don't get to see whatever sun is in front of, and so it depends on the seasons. That's enough for now. Let's move on now, finally, to starting to map, and we're catching up to people thousands of years ago. Map stars and those wandering dots carefully. We'll see again in chapter 3. Understanding this is critical to understanding these huge leaps, which really, in many ways, led to the scientific revolution, along with other societal things, political things, etc. And that scientific revolution informed the U.S. Constitution. So it affected humans a lot, right? There's your sky. There's where you are on Earth. And then there's the sky, in a sense, mapping stars, etc. But we're going to put it onto a map, and you know the name of that map, the Celestial Sphere. So, on to the Celestial Sphere, yay.